Now, based on what we have just discussed, we're going to continue to the other subtopic under this topic concept, which is called wave, sound, and light. Now, here we are going to discuss the transverse waves. We have already spoke about the pulse. We said that a pulse is a single disturbance that moves through a medium, right? That's what we said about the pulse. So this is a medium and this is a pulse. And then now, what is a wave? A wave, it is a regular repletion of pulse. Now, this is what is happening. When you take a rope and you only shank it only once, that's a single disturbance. You're going to form only pulse. But when you take a rope and you shake it multiple times, up and down, 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 what's going to happen is you're going to propagate a lot of pulses. But those lot of pulses, that repletion of pulses, we're going to call that a wave. It is no longer just a pulse, but combination of those pulses that you have just actually formed. We're going to call them a wave. That's how a wave gets to be formed. Now you can understand why this concept or this module, it is called wave, sound, and light. It's called wave because we had to build up to understand what does a wave actually look like. How do we know a wave? How do we see a wave? What forms a wave? We have just seen that wave can be pulse. Many pulses will form wave. So we were building on a wave. We started from the basics, okay? Now, as much as we have learned the definition of a transverse pulse, we still need to learn the definition of a transverse wave. Now, how do we define a transverse wave? We say that a wave in which the disturbance of the medium is perpendicular to the direction of the wave. This is the same as how we define a transverse pulse, but the difference is where you see a wave, we just say it's a pulse, all right? That's what is basically happening. So you have to understand that here, a wave, a medium will act perpendicular to the direction of the wave. Like for example, here we have a picture of a wave, right? Which is formation of many pulses. But you need to understand that the particles, the disturbance or the particles of the medium, they're gonna shoot upwards. As they shoot upwards, where is the wave moving? Wave is moving to the right. And we can see that the particles of this, they're going to shoot upwards right at this point to form a pulse, which is waves. We can see that these now are called waves because there are multiple of pulses. So we can see that the particles of this wave, it will most definitely act perpendicular to the direction of the wave because the wave is moving in this direction, which is to the right. It's moving in this direction while it is on the road. Now, every up and down movement past the position of equilibrium is called one complete oscillation. So every up and down movement past the position of equilibrium, is one complete oscillation. Okay, so that this definition can make sense to you, let me show you here. Say for an example, I'm gonna draw my Cartesian plane where I have y-axis and then this side I'm most definitely gonna have x-axis. When I draw a wave on my Cartesian plane, let me just end it here. 1, 2, 3. Okay. So this is a point, right? That I'm going to focus on to. Let me just write it like this. This is a point at which I am going to focus on to. I want to talk about oscillation. But firstly, let us learn how do we see a one wave? How do we see a complete wave? A complete wave is actually made up of two pulses, okay? When you have a Cartesian plane like this, and then you have something that looks like this, we can see that this is a pulse, right? And this is also another pulse. So two pulses, they form what we call a wave. They form only one wave. But most definitely, if I continue, this is another pulse, and this is another pulse. We have another wave. So how many waves do we have on this string or on this rope? We have two waves. So now we want to understand that how do we see that this is a one, so one wave, this is what I want you to understand again. One wave, which is this, what you see over there, it's one complete cycle. So one wave is the same as one complete cycle. I'm saying to you, this is a wave, but how do you know or how do you see that this is a one complete cycle? Now, to form a cycle, this is what we're going to do, right? What is this? From this point to that point, this is a pulse, right? I'm going to extract this pulse and I'm going to write it over here. This is this pulse. Now, this is another pulse. So I'm also going to extract it and write it over here. This is another pulse. And what you see over here, we have one complete cycle. So one complete cycle, it corresponds with one wave. So every up and down movement past the position of equilibrium is one complete oscillation. So if we are talking about this point, how many waves are going to pass through this point? 1, 2, 3. So meaning how many oscillations, that's what we mean. Oscillations are going to pass through this point. Up and down, the oscillations are going to pass through this point. So those waves, those complete waves, we call them the oscillations as well. So this is also an oscillation. So how many oscillations do we have? 1, 2, and 3. Okay, I hope that was clear. Now, we spoke about wave, right? As much as we spoke about pulse, what did we learn? We learned the length of a pulse. But here, we are also going to learn the length of a wave. From here to here, this is the length of a pulse because this is a pulse. From here to here, this is also a length of a pulse because this is a pulse. But from here to here, this will be a length of a wave. So this is a wavelength because this is one wave. So that means we have a wavelength. Another way to see a wavelength, let's have a look at this diagram over here. From this point to that point, we're going to have a wavelength. But how do you see that this is a wavelength? Remember what I said to you? I said one wave, it's a one complete cycle. So when you have a look at this diagram over here, from this point to that point, we can see we have a half of a pulse. This is a half of a pulse, right? I'm going to write it over here. And we also have a half of a pulse this side. I'm going to write it over here. And then we have a full pulse, which is this one. Remember, we are focusing from there to there. We have a full pulse, which is this one. I'm just going to write it over there. Now we have a complete cycle. So this is another way to spot out a wave. This is also a wavelength. So how do we see a wave? It's either we see a wave in this way, or we see a wave in this way. Okay, this is how we can see a wave. This is a wave, this is also a wave. You will also understand these things when you do mathematics under trigonometry, that this is a wave, this is also a wave. It's called cosine and this is called a sine, but it's fine. We'll learn that in mathematics. So that's how we see one complete wave. So now, Let us talk about these points over here. These are maximum, this is the maximum points, right? Because they are at the top. And these are minimum points because they are at the bottom. But you still have to understand that from rest position to the maximum point, from rest position to the minimum point, we are talking about the amplitude. Do not forget that. They still call the amplitude even here on the waves. So these maximum points, these peaks, these maximum points are called crests. These minimum points are called the troughs. Now, what is a crest? A crest, it is the highest point of a wave at its maximum displacement from rest position or from equilibrium. That is what you call the crest. The trough, which is these points over here, a lowest point of a wave at its maximum displacement from equilibrium in opposite direction, which is this. I hope everything was clear. Now, since when we are under the waves, this is what we need to learn, or this is what we need to understand. On a wave, or on waves, we have what you call the points that are out of phase. We also have the points that are in phase. Let us firstly talk about the points that are out of phase. What are the points out of phase? We say these points are not doing exactly the same thing at the same time. So if we spot the points that are not doing exact same thing at the same time, we can say those points are out of phase in this wave. So we have a wave, right? There is a wave. Here is a wave. Now let's spot, or let's look out for points that are out of phase. When you have a look at point C and point A, these 2 points on this wave, they are out of phase. How do we see that they are out of phase? They are not doing exact same thing. So how do we see they are not doing exact same thing? Now point A, it is moving along this line, right? Point C is also moving along this line. But when you have a look at point A is shooting upwards to the peak. Point C, it is shooting downwards to the peak. A is moving up, C is moving down. So now, for a fact that A it is moving up and C it is moving down, they are not doing the same thing. Hence why we say these 2 points are out of phase, because they are not doing the same thing. Now, let's have a look at other points which are out of phase in this wave. Now, let's talk about point D. Point D and point B, okay? Point D and point B. Point B, it is moving down from the peak. Point D, point B, it's moving down from the peak, and point D, it's moving up from a trough and a crest. B is moving down, that is moving up. They are not doing the same thing. The other one is going down, the other one is going up. So these 2 points are also regarded to be points that are out of phase. I hope it is clear how to note or how to spot the points that are out of phase. Now let's talk about the points that are in phase. Let me erase everything. Now, when you talk about the points that are in phase, these points, they are opposite of that. They are doing exact same thing at the same time and are equal distance from equilibrium position in the same direction. Now, let's talk about point A and point E. When you have a look at point A and point E, these 2 points, they are in phase. How do we see that? Point A is shooting up to the peak. Point E, it is also shooting up to the peak. These 2 points are mostly doing the same thing, exact same thing at the same time. Simultaneously, they go shoot simultaneously up to the peak. So that means these 2 points, which is A and E, we say they are in phase. Okay? Let's have a look at point B and point F. Point B is shooting down from the crest. Point F, it is also shooting down from crest. So that means point B and point F, they are doing exact same thing. Now these 2 points, they are considered to be the points that are doing exact same thing. Now for a fact that these 2 points are doing exact same thing, that means these points, we consider them to be points that are in phase, okay? Now, say for example, I include another point over here, right? So we have A, B, C, D, E, F, and let's say we have point G over there. Now, point G, it is in phase with which point? Point G is in phase with point C. When you have a look at point C is shooting downwards, point G is also shooting downwards. So that means these 2 points are in phase because they are doing exact same thing. I hope that was clear how to see or to spot out the points that are out of phase and the points that are in phase. And then that's it about some of the few things that we needed to learn about the wave, okay? Now let's go through these terms, the frequency and the wavelength. Now, what is a frequency? A frequency is the number of pulses that pass a point per second. We have many pulses that are formed through this medium. Now, if again, we spoke about oscillation. Let's say I'm going to focus on this point, right? I'm going to focus on this point. How many pulses are actually going to pass through this point, but within 1 second per second, within 1 second? How many pulses? I get these pulses are coming in this way. They're coming, these pulses, they're gonna pass through here. But I'll be counting how many pulses are actually going to pass through this point. Number of pulses that passed through this point within 1 second, we say, or we refer to that phenomenon as a frequency of a wave. So to determine the frequency of a wave, you need to know how many pulses passed through a point within 1 second. Now, a frequency of 4 hertz means that 4 waves passed point per second. What do I mean when I say that? Now, the units, apparently we can also calculate the frequency, but we need to know the formula that we use to calculate the frequency. Now, the formula that we use to calculate the frequency is this one, where we're going to say F will be equals to 1 over T. Now, this one, it actually simply means the number of pulses per second. So let's say how many pulses? 1, 2, 3, 4, 5, 6. So when we have 6 pulses, right? 6 pulses that are going to pass through this point in 1 second. 6 divided by 1, it will give us 6. So frequency will be equals to 6. But the units that we use for frequency, we call them hertz. So that means the frequency of this wave, it will be 6 hertz. If maybe these 6 pulses, they're gonna pass through this point in 1 second indeed. So therefore, it will be 6 hertz. That's why here they say the frequency of 4 hertz means that 4 waves pass point per second. Okay, we can take waves per se. The first wave, 1, 2, and 3. So that means we're gonna have okay, if you consider the number of waves, we're gonna say 3 divided by 1. So that means you're gonna have 3 hertz because 3, it represents number of waves. Okay, number of waves time. Yeah, so here it's gonna be number of waves, not number of pulses. Okay, we're gonna use number of waves. Actually, we have 3 waves. Yes, we have 6 pulses. That means we have 3 waves. So we're not gonna use this. Sorry, we're gonna use the number of pulses. Okay, all right. Now, what is a wavelength? Wavelength, it is the distance between 2 consecutive points in phase. We have already spoke about that. Now, when you have a look at this point, And these 2 points are in phase. And I showed you, or I told you that this is another way to spot out a wave, right? I told you this is another way to look at a wave. So these 2 points are in phase because they are doing exact same thing. Remember that. So this one will move down, this one will also move down. So that means these 2 points are in phase. And a wavelength, we can also look at it through the points that are in phase. And then because this is a length, the units that we use is in meters. Okay. And then the formula that we use to calculate the wavelength, it's velocity or the speed of the wave is equals to wavelength. Let me do this. We're going to say is equals to the wavelength multiplied by the frequency. Okay? So what is this thing? It's called lambda. This Greek symbol, it is called lambda. Okay, it is called lambda. It represents the wavelength. So the wavelength, which is given by lambda, it is measured in which units? In meters, which is the wavelength. So the formula that we use to calculate the wavelength, it is this one over here. It depends on the frequency that we have just calculated and the speed of the wave. Okay, and therefore now we can determine the what? The wavelength of this wave. Okay, I hope that was clear.